In this video, we're going to talk about the continuity of functions of two variables. The function f is continuous at the point AB, provided the following conditions are met. 1. The function f is defined at the point AB. 2. The limit as xy goes to AB of f of xy exists. And 3. The limit as xy goes to AB of f of xy is equal to f of AB by direct substitution. A function of multiple variables will be continuous at a point as long as its limit is equal to its value at that point. This definition for continuity applies at boundary points of the domain of a function, provided the limits in the definition are taken along paths that lie inside the domain for that function. Rational functions, polynomial functions, trig functions, log functions, and exponential functions, these are all continuous on their respective domains. Let's work an example. I want to determine at which points in two-dimensional space the following functions are continuous. The first function is given by f of xy is equal to xy divided by the quantity x squared y squared plus 1. The second function is f of xy is equal to the quantity x squared plus y squared over the quantity x times the quantity y squared minus 1. In the first case, I have a rational function. Rational functions are continuous over their entire domain. This particular denominator can never equal 0 because I'm squaring the x and y values. This means that my function is continuous over all two-dimensional space. In the second case, I again have a rational function, and these are continuous over their domain, but the domain for this function includes all of two-dimensional space except for x is equal to 0 and y is equal to plus or minus 1. This means that this function is continuous over all of two-dimensional space except for those two values. I cannot let x equal 0 or y equal positive or negative 1. Let's look at continuity when I have functions that are composed. If u is the function f of xy and it is continuous at AB, and v is equal to g of u, which is continuous at g of AB, then the composite function z is equal to g composed with f of xy will be continuous at the point AB. Let's look at an example. I want to find the points in R2 where f of xy is equal to the natural log of x minus y is continuous, and I want to find the points in R2 where f of xy is equal to the piecewise defined function given by the quantity 1 minus the cosine of the quantity x squared plus y squared divided by the quantity x squared plus y squared, where xy is not equal to 0, 0, and it's defined to be 0 when xy is 0, 0. For f of xy is equal to the natural log of x minus y, this function has a domain of all xy provided x is greater than y, so that the function is continuous on R2 for all x greater than y. In the second function that is piecewise defined, we notice that the quantity 1 minus the cosine of x squared plus y squared over x squared plus y squared has a domain of all R2 except for the point 0, 0. But then I go ahead and define the function value to be 0 when xy is 0, 0. This means that my function will be continuous over all R2. Now let's look at functions of three variables. If I have functions that have more than two variables, we can simply extend all of the definitions and limits that we've done for functions of two variables to functions of three or more variables. Let's look at an example. I want to evaluate the limits of functions in three variables. I want to evaluate the limit as xyz goes to the point 1, 1, 1 of the quantity x minus the square root of xz minus the square root of xy plus the square root of yz divided by the quantity x minus the square root of xz plus the square root of xy minus the square root of yz. I also want to evaluate the limit as xyz goes to the point 1, negative 1, 1 for the quantity xz plus 5x plus yz plus 5y, all divided by the quantity x plus y. So in the first limit, I am going to use factoring by grouping. I'm going to rewrite my limit as the limit as xyz goes to the point 1, 1, 1 of the quantity square root of x times the square root of x minus the square root of z minus the square root of y times the square root of x minus the square root of z, all over the quantity square root of x times the square root of x minus the square root of z plus the square root of y times the square root of x minus the square root of z. I'm going to factor out the greatest common factor and simplify. This gives me a limit as xyz approaches the point 1, 1, 1 of the quantity square root of x minus square root of y times the quantity square root of x minus square root of z, all divided by the quantity square root of x plus square root of y times the square root of x minus the square root of z. The term square root of x minus square root of z cancels in top and bottom, and I can use direct substitution now. I get 1 minus 1 over 1 plus 1. This is 0 over 2, or 0. In the second limit, I'm also going to use factoring by grouping, but this time I only need to use it in the numerator. I get the limit as xyz approaches the point 1, negative 1, 1 of the quantity x times z plus 5 plus y times z plus 5 over x plus y. I'm going to factor out the z plus 5 in the top, and I get the limit as xyz approaches the point 1, negative 1, 1 of the quantity x plus y times the quantity z plus 5 over the quantity x plus y. The factor x plus y cancels in top and bottom, leaving me with the limit as xyz approaches 1, negative 1, 1 of z plus 5. I can now use direct substitution and plug in 1 for z. I get 1 plus 5, which gives me a limit of 6. Now you get to try it. Pause the video and evaluate the limit as xy approaches 0, 0 of y squared over the quantity x to the 8th plus y squared. When you're ready, restart the video to check your understanding. As I look at this limit, it's a function in two variables, and I note that it's a rational function, which means it is continuous over its domain. In this case, the domain for the function is all values of R2 except for the point 0, 0. But if I plug in 0, 0, my direct substitution gives me an indeterminate limit. This means I'm going to have to look at this a little more closely. Before I start spinning my wheels and trying to figure out how to find a limit for this indeterminate form, I might want to check to see if the limit exists. So I'm going to say what happens along path 1 where y is equal to 0. I'm going to take the limit as xy approaches 0, 0, where I hold y constant at 0. This means I'm taking the limit as x approaches 0 of 0 over x to the 8th. This is a limit of 0. I might want to think about letting x be held constant at 0, but when this happens, I get an indeterminate form in my limit again. So I'm going to have to pick something else. In this case, I notice that I have y squared and x to the 8th in my function. So if I let y equal x to the 4th, my limit becomes the limit as xy approaches 0, 0 of x to the 8th over the quantity x to the 8th plus x to the 8th. This gives me a limit of 1/2. Notice I looked at my function to find something that would give me a very simple limit to evaluate. But I get two different values along two different paths. The two-path test shows me that the limit does not exist, and I'm done. Be sure and let me know if you have any questions about using what we know about continuity to help us find limits of functions of two or more variables.